Hi, and welcome to a supplementary lecture covering the van der Waals equation of state and the Maxwell construction. What I've got plotted here are three curves, three plots of the van der Waals equation of state, pressure versus volume, for three different temperatures. And the van der Waals equation of state, as you've read about, is the simplest equation of state that takes into account interactions between the fundamental particles, the atoms or molecules that constitute a fluid. In physics, fluids refer to both gases and liquids. A fluid is literally anything that flows. And to the right here, over on the high volume part of this plot, the van der Waals equation of state is describing a gas. Right? A gas occupies a large volume. And as we start on the right and move to the left, in other words, as we imagine compressing the gas, and let's follow a line at constant temperature. So we are isothermally compressing the gas, which means, for example, we have a cylinder with a piston and we slowly push the piston in, compressing the gas. We have to do it slowly to maintain the same temperature the whole time. If we do it quickly, the gas heats up. You know this when you pump up car tires or pump up bike tires, right? If you pump in a piston quickly, the gas heats up. So what we need to do is pump it in slow enough that any increase in temperature is allowed to dissipate. The heat has enough time to flow outwards into its surroundings, and therefore for the system to remain in thermal equilibrium with its surroundings, which act as the heat bath that keeps the temperature constant. So as we move towards smaller volume, we push the piston in, we see that the pressure goes up. It goes up slowly, but it goes up. And again, this is consistent with observation. As you compress gas in a bike pump, the resistance you feel to compression increases the more you compress it. So the pressure inside is getting higher. So this line here describes a gas, and it obeys what we intuitively expect from a gas being compressed slowly. The problem arises when we reach the top of the curve here, this maxima, and we start to go downhill. So what's happening now is we are compressing the gas further, but the pressure is decreasing. This is unphysical. This is not what we observe to happen. Right? This would mean that at a certain point, as you compress your bike pump, it would suddenly stop getting harder and get a lot easier again. And in fact, it will get easier and easier at a larger and larger rate because the slope of this line is increasing. It's getting more positive. So what you would feel is some sort of suction. The pressure gets less. It gets much and much easier to compress the pump, and you would just keep going until you hit zero volume. That's not what happens in real life. That weird behavior is rectified once we hit the minimum and start moving upwards again in pressure. But now we see the pressure is increasing much, much more rapidly as we compress the system. Much more rapidly than it was when we were describing a gas. So the interpretation here is that this part of the curve describes a liquid. Right? A liquid is known for its pressure to increase very rapidly when you try and decrease its volume. That's why a liquid is much harder to compress than a gas. So we have three regions of this curve, one of which seems to describe what we expect for the behavior of a gas, and that's all on the high volume end. On the low volume end, we've got behavior that is what we expect of a liquid. But then joining the two, we have this unphysical region where the pressure decreases as you compress the fluid. Right? That doesn't happen in nature, so this bit of the curve is not fit to describe physical systems and needs to be replaced by something else. And the thing that it is replaced by is the so-called Maxwell construction. And we need to understand physically what the Maxwell construction represents. So let's switch to a depiction of the Maxwell construction. Okay, so on the right-hand side, we have a particular van der Waals equation of state at constant temperature. And you've got plotted here the maximum and the minimum. And what we've got here, so we've got the gas phase coming up here, the liquid phase here, and the Maxwell construction is just a horizontal line that joins some point in the gas phase with some point in the liquid phase. And this is the trajectory that corresponds to what happens in real life. So let's imagine compressing the gas again, and let's try and understand what this horizontal line represents. So we compress the curve continues off the graph here on the right. Coming from the right, coming from high volume, we compress the gas, and then we reach this point here. And then we keep compressing the system, but the pressure no longer changes. What is happening here is that at this point, when you compress the system further at constant temperature, what happens is that some of the gas starts condensing into a liquid. So a fraction of the system starts becoming liquid, and that fraction grows as you move along this curve from the right to the left. So over here, you may have, say, 90% of the gas by mass, say, or the fluid by mass is a gas, and 10% is liquid. Whereas over here, you'll pass a point where 90% is liquid, 10% is gas. So at each point along this horizontal line, the liquid and the gas are existing in equilibrium. Like, what is happening is that the rate at which gas is being condensed into a liquid is matched by the rate at which the liquid is evaporating into a gas. Incidentally, don't worry about the funny units in these graphs. This is 1 divided by density, which is equivalent to volume. This is actually a plot for a gas of neutrons and protons, which is not your everyday kind of gas, but it turns out it behaves pretty similarly. But don't worry about the units, focus on the phenomenology. We call this horizontal line the liquid-gas coexistence trajectory. At every point along here, you have not just a single liquid or a single gas, but both at the same time. And that's the problem with the van der Waals equation of state. It can only describe either a system of all liquid or a system that is all gas. But in real life, there exists temperatures, densities, and pressures in which liquids and gases can coexist. And that physics is not captured in the van der Waals equation of state, and that is what the Maxwell construction corrects for. That's what this horizontal line is. So the next question is, well, how do you figure out where this horizontal line goes, right? Why did I place it here and not, say, further up here or further down here? What determines that? Well, there's a fairly simple argument, a theoretical argument in terms of energy conservation. We learnt earlier in the semester that the work done compressing a system is equal to the area under the curve along the trajectory in the pressure-volume plane. So in other words, if I move along this trajectory here, from the far right to the minimum, then the work done compressing the system is just equal to this area here. Okay, so suppose for example, I was able to maintain the system as a single component gas up to here and a single component liquid down here, and I was able to compress it along this curve, and then I decided to decompress it along this curve, and I came back to this point here. So I've done some work on the system, compressing it, and then the system has done some work on me, decompressing it. Conservation of energy says that the total work done has to be 0. Right, otherwise, I could go around this trajectory and get some net amount of work out, which I could use to power my perpetual motion machine, which unfortunately I can't. So I need to make sure that the area under this curve matches the area under this curve. And that is the thing that dictates where I put this horizontal line. I place it such that the area under the horizontal line matches the area under the blue line. Or in other words, the area between the green horizontal line and the blue line above it in this region here is equal to the area between the horizontal green line and the area and the blue line below it here. So this area and this area have to be equal. So I can figure that out. I can do a bit of math and figure out where to place the green line, and this is at a particular temperature. And this gives me 2 densities. It gives me the density or the volume here, where the horizontal line starts, and the density where it ends, right? And this is just for this temperature. So over on the right-hand side, what I could do is I can plot the temperature as a function of density. I could plot this point here and this point here at this particular temperature on this graph here. And the movie I'm about to show you shows what happens when I change the temperature and therefore change this blue curve. You'll see that the green horizontal line changes, and therefore the density or the volume at which you get the pure liquid phase and at which you get the pure gas phase change with it. So let me play this once so you can see how it works. So this is happening a little slowly, but you can see that as I increase the temperature, this whole blue curve shifts upwards, and the horizontal line moves slightly upwards in volume at the left-hand end and downwards in volume at the right-hand end. If I stop it here, this point here, which is a volume here, if I turn it into a density, becomes this point here. So this blue curve is the van der Waals equation of state at a temperature of around 26 MeV. Again, don't worry about the funny units here. MeV, mega electron volts, is a unit of energy, but I can turn it into a temperature by multiplying it by Boltzmann's constant. This is something that you'll become a lot more familiar with in the last 2 weeks of this course. But this is just the temperature at which the equation of state looks like this. And at this temperature, the liquid and the gas coexist between this volume and this volume, which is the same as between this density and this density. And as I increase the temperature, that density region becomes narrower and narrower. And what we're plotting over on the left-hand side is the liquid-gas coexistence curve. Okay, so this shows, as a function of temperature, the range of densities you will put your system at for it to exist as a liquid in equilibrium with a gas. To the right-hand side of this, you've got a pure liquid. To the left-hand side, you've got a pure gas. In the middle, you've got a liquid and a gas coexisting. And what you'll notice is that it rises up and tapers to a point, and that's the point at which the maximum and the minimum in the van der Waals equation of state disappear and turn into this point of inflection here, above which there is no longer a maximum or minimum. There's no longer the physical problem with the equation of state, and we have entered a region where the liquid phase and the gas phase are the same phase. They are indistinguishable from each other. So this is the so-called critical point of the liquid. So to conclude, what I'd like to do is actually show you some simulations of a fluid that is being simulated under the van der Waals equation of state. And I want to use this to just illustrate physically what is going on with the liquid-gas coexistence curve. So here's the coexistence curve at a plot of temperature versus density, and at each temperature there are two densities. The higher density is the liquid phase, the lower density is the gas phase, and in between is the region in which liquid and gas coexist. What we do is we take, this is a two-dimensional simulation. This is just some region of space. It doesn't matter what the volume, what the units are in this case. And we just randomly initialize the space with densities above and below some average density. We're going to evolve the system from identical starting points at 25, 27 and 28.5 MeV temperatures. So for the purposes of this, you just need to know this is lowish density, intermediate and high density close to the critical point here. So let's go ahead and play the simulation. And so what we see is that on the left, the fluid decomposes into the blue regions, which are regions of higher density in this case, and red regions, which are regions of lower density. So the blue corresponds to liquid, the red to gas. So we see that what happens is the fluid naturally wants to separate out into regions where there's just gas and regions where there's just liquid. At a higher density, a similar thing happens, but you'll see that the contrast in density between the high and the low density phases is much less. Right, so the redder something is, the lower density it has, the bluer something is, the higher density it has. Here it's a lot fuzzier and it's a lot, the distinction isn't so sharp. The high density fluid is at a lower density and the low density gas is at a slightly higher density. So that corresponds to a temperature of around 27 MeV here compared to a density of 25 MeV around here. And then finally, in the last simulation cannot settle upon a liquid and a gas phase at all. In fact, apart from small statistical fluctuations, the density here is very homogeneous. Okay, so although you can see little fluctuations, they are very, very small. So this is essentially at a constant density, and this does correspond to the critical temperature of 28.5 MeV. So this is a density at which if you start some of the fluid off as a liquid and some as a gas, the gas increases in density, the fluid decreases in density until it merges into one single fluid. The distinction between liquid and gas has been lost.